Newton's law of gravitation. The gravitational force between two bodies, 1 and 2, is F12 equal to g m1 m2 over r square, with m1 m2 are the mass of the bodies. R is the distance between the bodies, and g is the universal constant. The constant has values of 6.67 times 10 to the power negative 11 Newton meter square per kg square. Remarks. First, gravitational force are action and reaction pair. That is, the force on 1 F1 and the force on 2 F2 both are equal in magnitude but opposite in direction. Therefore, F1 equal to negative F2, and both the values of F1 and F2 are equal, which is equal to F between 1 and 2. Second, gravitational forces are attractive force. Third, gravitational force is inversely proportional to the square of the distance between the two bodies. That is, if we plot a graph of gravitational force and separations, we got a graph like this one, with force proportional to 1 over r square. The greater the distance between the two bodies, the smaller will be the resulting gravitational force. Let's look at some examples of gravitational force. First case, the gravitational force between a girl and a boy of mass 20 kg and 15 kg, and the distance between the two bodies is 1 meter. By using the equation F equal to g m1 m2 over r square, we have the gravitational force on the girls and on the boy are the same, which is equal to 2 times 10 to the power negative 8 newtons, which is very small, or we can negate this force. For the second case, let's consider the gravitational force on a boy on the Earth's surface. By using the equation F equal to g m1 m2 over r square, the mass of the Earth is 5.98 times 10 to the power 24 kilogram. If the mass of the boy is equal to 15 kg, and the distance between the boy and the Earth is in fact the radius of the Earth, which is equal to 6,400 kilometers, then the gravitational force acting on the boy is equal to 6.67 times 10 to the power negative 11 times 5.98 times 10 to the power 24 times 15 over 6.4 times 10 to the power 6 square, which is equal to 146 Newton. In fact, this gravitational force acting on the boy is what we say the weight of the boy. Another example, let's consider the gravitational force acting on a satellite at a distance of 1.2 times 10 to the power 7 meter from the Earth's center. If the mass of the satellite is 2000 kilograms, then we have gravitational force acting on the satellite equal to 5,540 Newton. Let's consider the satellite orbiting around the Earth. For a satellite revolving around the Earth in a circular path, the satellite has a centripetal acceleration AC towards the center of the Earth. The centripetal acceleration is equal to v squared over r or omega squared r. By Newton's second law, F equal to ma, there must be a centripetal force on the satellite such that it has centripetal acceleration. What is the origin of this force? Obviously, this centripetal force is provided by the gravitational force F acting on the satellite due to the presence of the Earth, with F equal to g me ms over r squared. At any position, the gravitational force is directed towards the center of the Earth. Remarks. First, the gravitational force is the only force between the Earth and the satellite to enable the satellite to perform circular motion. Second, the direction of the gravitational force on the satellite must lie on the plane of the circle. Therefore, the plane of the circle must also pass through the Earth's center. Now let's go through orbital speed v and orbital period t. When a satellite of mass m circulating around the Earth at a distance of r from the Earth's center, let me be the mass of the Earth, v be the orbital speed, t be the orbital period. By F equal to ma, we have g me m over r squared equal to m v squared over r, implying that the orbital speed equal to square root of gm over r. And the orbital period t can be found by 2 pi r over v equal to 2 pi r square root r over gm. Weightlessness 無重狀態. When an astronaut 太空人 is inside a satellite orbiting around the Earth with a speed v, he is in a state of weightlessness. Can you explain why? Let's look at an analogy. Means 對照. For the case of a man standing inside a lift which is connected by a cable. The force acting on the man is his weight, or we say the gravitational force acting on him by the earth, which is his weight, we call mg. Another force is the reaction force, which is the force acting on him by the fall of the lift, r. If the cable is broken, the lift and the man falls with the same acceleration, which is equal to acceleration due to gravity. In this case, the net force acting on the man is equal to mg minus r, which is equal to ma mg minus r. We have, since A is equal to G, therefore we got the reaction force acting on the man, R, becomes 0. Therefore, we say he is in a state of weightlessness. Simply speaking, the man is in a state of weightlessness, that is R equal to 0, when both the man and the supporting surface, the lift, are moving with the same acceleration, which is equal to the acceleration due to gravity. Now back to the case of the satellite moving around the Earth in a circular motion with speed v. For the astronauts inside the satellite, there are two forces acting on him. The first one is the gravitational force acting on him by the Earth, which is equal to mg. The second force is the reaction force, the supporting force acting on him by the satellite's inside surface. The resultant force acting towards the center of the Earth is F equal to Fg minus R, equal to the mass times the centripetal acceleration, A. And because Fg equal to ma by gm em over r square equal to mv square over r. Fg is this one, ma is this one. Since Fg is equal to ma, therefore the reaction force becomes 0. That's why the man inside the satellite is weightless.